All right, so Prop 19 is closely related to Prop 18. And if this is maybe your first time going through any kind of rigor, like being introduced to mathematical rigor, it might seem a little bit redundant. It might seem a little bit strange, Prop 19. So Prop 19 says in any triangle, the greater angle is subtended by the greater side. So it's saying that if you take, in any triangle, if you take two of the angles, say B and C, whichever one of those angles is larger, the side that is opposite that angle is going to be the larger side, right? So if we look at B and C, B is fairly clearly a larger angle, so the side that is opposite B, AC, is going to be longer than the side that is opposite C. So the claim here is that if B, angle B, is greater than angle C, then AC is greater than AB. And just kind of really quickly, the reason I say this might feel redundant is because if you remember, Prop 18 is the other direction of this. Prop 18 says, in any triangle, the greater side subtends the greater angle. So just kind of like really quickly, the logic here is Prop 18 is saying something along the lines of, let's see, and how did we do it? We did AC, yeah. So Prop 18 is saying that if AC is greater than AB, then, let's see, AC would be opposite B. Then angle B is greater than angle C, right? So if AC is longer than AB, then angle B is greater than angle C. That's what Prop 18 is saying. Prop 19 is the other direction of this. So in 18, the hypothesis is that AC is greater than AB, and the conclusion is that angle B is greater than angle C. 19 is the other way. If angle B is greater than angle C, then AC, side AC, is greater than side AB. So these two work together as a biconditional, but it's the two different directions of a conditional statement. So of a biconditional statement. So when you have a biconditional like this, like 18 and 19 could be combined into an if and only if statement that says something like AC is greater than AB if and only if angle B is greater than angle C. But when you have a bidirectional statement like this, you have to prove both directions. So now we're proving the reverse direction of that bidirectional. All right. So how does it work? Right, so we say consider any triangle ABC and assume that angle ABC is greater than angle BCA. So ABC is greater than BCA. All right, so the claim then, what we need to show is that side AC is longer than AB. And it's an interesting argument. I guess it's technically an argument that is, it feels like a contradiction argument, but I think that it's maybe more appropriately like a pigeonhole argument. So we're saying basically, well, if, let's see, if AC is not greater than AB, two cases. Right? If AC is not greater than AB, then there are two possible cases. Case one is that AC equals AB. Case two is that AC is shorter than AB. So the two cases are either AC is exactly the same length as AB or AC is shorter than AB. So we'll look at both of these cases and see that a contradiction arises from both of them. So case one, assume that AC equals AB. Well, what do we know about that? What can we say about the corresponding angles if AC is equal to AB? Well, if AC is equal to AB, then ABC is an isosceles triangle. And we know something about angles at the base of an isosceles triangle. So then then it follows that angle ABC equals angle BCA, and this is from Prop 5, which says that the angles at the base of an isosceles triangle are equal. But that's a contradiction. Why is it a contradiction? Because at the outset we have assumed that this is a fixed truth. Angle ABC is greater than angle BCA. So we've just found that, well, if we make the assumption that AC is equal to AB, then we arrive at a contradiction, which is saying that angle ABC is actually equal to BCA. So that can't be the case. So we can rule that out. Well, that only leaves then case 2, which is that AC is shorter than AB. But, and let's see here, I'm just going to look at what's written here, because it says, Euclid kind of does it a little bit differently, because after saying, all right, well, this would be a contradiction, assuming that AC equals AB, it leads to a contradiction, then he goes on to say, well, neither is AC less than AB, for then the angle ABC would also have to be less than angle ACB. Why is that true? Well, we have a proposition. So case 2, if AC is less than AB, then angle ABC would be strictly less than angle BCA by the previous proposition. Because the previous proposition was the one that said that, all right, well, the greater side subtends the greater angle. So if AB is greater than AC, then AB is opposite the greater angle, which is C. But, again, this is a contradiction, right? Because at the outset, we have assumed that this is a fixed truth, that ABC is definitely greater than BCA. So, again, which is a contradiction. So in either of those cases, you arrive at a contradiction. Let's see, how should I say it? Thus, it must be the case. It must be the case that AC is greater than AB. Right? Yeah. So therefore, AC is not less than AB. It was proved that it's not equal either. So AC is greater than AB. QED. Therefore, etc.